Hello, everybody. It's Scott McCullough with Vector Corrosion Technologies, your favorite webinar moderator. Welcome to the Webinar Wednesday hosted by the Concrete Preservation Alliance. This is a bridge preservation webinar series. It's been running for 9 months so far, since last August, and we have 3 more sessions to go. We have a great presentation for you today focused on impressed current cathodic protection with our good friend Matt Miltenberger. So we'll get this show on the road right away. The Concrete Preservation Alliance, as you know, is a network of organizations committed to advancing best practices in concrete preservation and infrastructure renewal. And we draw from our member organizations to deliver these presentations and these educational sessions for you. So here's a list of our current members. Wide-ranging across the globe, and we thank them for participating and for sharing the message of saving structures. The home of the Concrete Preservation Alliance is wesavestructures.info, and if you've registered for this webinar, you probably know that. So you found your way to the events tab right there, where you can register for this and any upcoming webinar series. This session will be recorded, and the recording will be posted at the very bottom of the events tab that is displayed on the screen right here, along with the slide deck of today's slides and all the other presentations that we've done. So please visit often and register for more webinar series. Without further ado, we'll turn it over to our good friend Matt Miltenberger. Matt is the Vice President of VCS, and he is a licensed professional engineer in 12 states and is a NACE certified cathodic protection specialist. He has over 35 years of experience in the concrete industry. His areas of expertise include concrete evaluation, concrete materials, service life modeling, and corrosion mitigation. Matt started his career in commercial construction way back in the 1980s, worked as a material specialist trainee for the Federal Highways Administration in the United States, as a research engineer for Master Builders Technologies, as a concrete durability consultant for Kearney Consulting Group, and now conducts concrete rehabilitation and corrosion mitigation design as a CP specialist for VCS. Now, I have it on good authority today that Matt got a COVID haircut just for this presentation for you. So he is helped me welcome the George Clooney of concrete restoration, Matt Miltenberger. He's going to talk to us today about impressed current cathodic protection. And over to you, Matt.
What we're going to talk about today is we're going to go over a few little historical pointers for cathodic protection of concrete bridges, kind of where the technology developed and how it progressed. We're going to go over corrosion basics and trying to understand the difference between galvanic current cathodic protection and impressed current cathodic protection systems, and then go over the installation of modern impressed current cathodic protection systems in general. So the fundamental thing that I want to show you here on this slide is we're dealing with corrosion, and corrosion has both an anode and a cathode. And you can see a nice clean, if you see my pointer, you see a nice clean fresh rebar with this mill scale, and just an inch or two away you see actively corroding rebar, and you see a reinforcing tie that goes from the top over the bottom steel, and you can see that they have corrosion and fresh good rebar. In this area here we call the cathode, and this the anode. So anode is where rust forms in a natural corrosion cell. So excuse me, what we do in trying to stop that corrosion cell, we have to try to use a couple techniques to stop the corrosion cell from transferring current between the anode and cathodes. And in order to do that, we use a galvanic corrosion protection system. We could use impressed current cathodic protection system, or we could use electrochemical treatments. So originally, corrosion protection in most all of its forms has been galvanic. They figured out back in the 1800s that you can use zinc to protect steel from corroding. So you use zinc and you tie the two metals together electrically, and they're in an electrolyte, be it water or soil or concrete. Current transfers between the two different metals, and you basically create a low voltage battery. And when you hook up a galvanic anode to a structure, you have very little maintenance. It just does its thing. It corrodes the sacrificial metal, the more active metal. In pipelines or marine applications, you would most of the time use one of three metals: magnesium, aluminum, or zinc. You want to, in concrete, you want to just use zinc, because even in concrete, zinc will passivate, and it won't give you any current if it is not active. So what we do is we activate the zinc with an alkali material. So typically you're going to have a small localized corrosion protection system for concrete repairs using galvanic corrosion protection. If you want to protect the whole structure, it's more cost effective to use impressed current cathodic protection. And when you do this, you're bringing in external power. That external power provides DC current to the reinforcing steel through an anode, and the anode is either a metal or a ceramic, or that we'll get into a little bit down the road here. But the key is impressed current cathodic protection allows you to adjust the power of the battery up or down as needed, so that you're balancing the corrosion current that you need, and you don't overprotect or underprotect. It gives you some ability to adjust. That's the key to impressed current. And most impressed current cathodic protection systems, in the modern ones, can last 50 plus years. And then we have electrochemical treatments, which is kind of like an impressed current cathodic protection system with a temporary anode that is run at a lot higher current density, which means it changes the chemistry of the concrete around the reinforcing steel, making it more, it kind of turns the clock back on the corrosion cell. And once it repassivate the steel, what you want to do is protect it against recontamination if you use electrochemical treatments. So those are the three things, the three types of corrosion protection systems. What we're going to talk about is this middle one, impressed current cathodic protection. So fundamentals, let's make sure we get this part straight. What we have in a corrosion cell is the anode. Remember that first picture with the rust, that's your anode. The bare steel, that's your cathode. You have a metallic path, and that's the piece of reinforcing steel between the two. And then you have an electrolytic path, and that electrolytic path can be water, soil, concrete. It can be jello. It can be anything that will transfer electrons between the anode and the cathode. My screen just went blank. Okay, here we go. I'm going to back up. All right. So here is the corrosion circuit. We went over the anode, cathode, metallic path, and electrolyte. Well, the chemistry that occurs at the anode is the oxidation of iron. So iron will be your reinforcing steel in a solid will be dissolved and turned into an ion. And a ferrous ion is Fe2, ferric is Fe3. And then you release electrons. They run through the reinforcing steel to the cathode, where you reduce oxygen. When you reduce oxygen, you gain electrons, you have some water, and you create hydroxyl ion. Hydroxyl ion increases the pH in the area around the cathode. So this also sort of repels the chlorides. And then to complete the circuit, you have the ionic current that flows through the electrolyte. And that electrolyte is either concrete, soil, or water. What we do with cathodic protection design is we're really designing a corrosion protection system based on this circuit. And this circuit you see here is the difference between your anode, your anodic location. It'll have a potential of around 400, but give or take, 50 millivolts. It can even go up to 500 or 600 on occasion if you're really corroding fast and there's not much oxygen. That can go down to about 600. And then you have the cathode, or the passive steel, which is the normal condition, like when you start you put rebar into concrete. There's no chlorides. It gets happy. It's sitting there in this alkaline environment. It initially corrodes and creates a passive oxide film that's on the surface, and the potential of that bar becomes around 200 millivolts or above. It can be positive 100 millivolts copper sulfate electrode. That's what CSE means. So between the cathode and the anode, there's a voltage difference. And there is the resistance of the reinforcing steel, which is very small, but the concrete resistance is in the way. So that completes the circuit. That's this ionic path. So when the concrete gets wet, the resistance of the concrete goes down. And so what happens is the voltage difference between the anode and cathode is fixed, is relatively constant. So when you have a lower resistance, you get a higher current. So you have more corrosion when it's wet, less corrosion when it's dry. That all makes pretty much a lot of sense to most people. If you ever observe it in the real world, you'll realize that there's these little water droplets, and on these little water droplets, you'll see rings of corrosion that occur around the perimeter of the steel. So then what is cathodic protection? Well, we're providing corrosion control by throwing external current onto the metal through the electrolyte, and you force the steel to become a cathode. The entire element becomes a cathode. So you reverse the corrosion at the anode and you reinforce the cathode areas. And that is the same process, whether it's galvanic or impressed current. So now we had that other little corrosion current that was the corrosion circuit that you can see down on the bottom here. You have, when the anodic steel becomes cathodic, the potential difference between the two locations is 0. So there's really no current flowing through the bottom loop. The external anode, which is being supplied a Either it's a zinc, or it's magnesium or aluminum, or it's an external impressed current anode with a variable voltage, will throw current, and it will throw current to the steel, and it will reverse the anodic corrosion current, and so that it stops the corrosion reaction on the steel. The external anode has to produce more current than the native corrosion rate in order for it to stop the corrosion cell and polarize the reinforcing steel. Those are terms you're going to hear a little bit later on in the rest of the discussion. In both cases, we also have this electrolyte resistance. So this electrolyte resistance will determine how much voltage you have to deliver to provide to deliver enough current for the corrosion cell. In reality, what we are doing is you have this reinforcing steel, and it's encased in concrete, and you're either going to place an anode on the surface, or you'll place an overlay and you'll embed it in the overlay, or you're going to install the anode into the concrete, and so the anode will throw current to the reinforcing steel from inside. And when you do that, you have some wiring that's involved. Well, when we add the wire into the circuit, you have your reinforcing steel, you have your anode, you have your power supply, you have some wiring that's involved, and then you have the concrete resistance. And this concrete resistance will fluctuate with moisture and temperature in the real environment. So this has to be considered over a range when you're doing your design. Well, so sorry about the back and forth on the slides here. When cathodic protection was being installed on bridges in the beginning, back in the early 70s, they started doing some experimentation with conductive paints and conductive overlays, and then they got into slot systems. And what they started out with were these conductive overlays using technology that they've been using in soil and in boats, in marine structures. They're just applying that to concrete bridges, and it didn't work out as well as they thought. But they did a bunch of installations with the Federal Highway, and they got to a certain point where they learned a few things. Well, here's what the very first type of system involved. They have all these pancake anodes, which is silicon iron that is wired together in a string, and they would place these down the middle of the road, and then they would put a conductive asphalt overlay on top of it and buried all these wires in with it. Well, that worked out well until they milled the overlay up and ripped up all these wires, or you've run the system too hot, and the anode itself starts to corrode and cause a pothole at each one of these locations where an anode was. There would be a pothole there. The asphalt would blow up like this. So in soil, the anode can expand, but it won't cause a problem structurally. But in concrete, because concrete is so dense, and with asphalt it's pretty dense, it will cause the structure to break apart, cause the material to break apart. So then they said, well, let's switch over and we do some slots. We can cut these slots with a saw, And then we can put a wire in there and we can fill it with a conductive grout, or we can use a graphite. This is a graphite conductor, and we can fill the slot with a grout, or then they use mixed metal oxide coated titanium. That's what this is down below. And this is a ribbon anode. So essentially, what they started out using was this titanium wire, and they put it in to these slots and they poured the grout on top of it. Well, they didn't have great quality control, and the ribbon, the wire was eventually found its way down to the bottom of the slot. It didn't get coated by the polymer, and it acidified the concrete, because when you break down water, acid is formed at the anode if this gets moist. And because it wasn't embedded in the grout, this is the kind of situation that will occur, and then the concrete breaks apart, and then the grout comes out of the slot. So that was basically an installation defect that they learned the hard way. They also found that if it's improperly designed or installed, you can have some real issues. If you run it too hot, you get the same thing with acidification along the anodes. If you have a short circuit, or there's a really close reinforcement bar near one of these slots, it'll dump current, and when it dumps current, it will acidify. So this acidification is the biggest problem that they had with these initial slot systems. And they came up with a current density that will pretty much eliminate that acidification problem in current practice. Also, they were running these with relatively small zones, and so that increases the driving voltage. The small size of the zones increases the driving voltage. When you increase the voltage that's being delivered to get the current to the steel, that also produces more reactions at the anode. So the lessons are: proper design, installation, and maintenance is required for a long-term effectiveness. And rectifiers do not like lightning. They would get hit and get knocked out. And they also found out that vandals like to steal the copper from the installation. So your low voltage wires would get cut and removed from the structure and scrapped. That was really those are some problems that still exist. Lightning has ceased to occur, and vandals are still out there. We did learn that inert anode materials are required for concrete. It's because of the acidification I was talking about. And the inert anode materials that we're talking about are these mixed metal oxide coated titaniums and ceramic anodes, which we'll go into next. The wiring connections have been identified as the weak link. You can have a rectifier that's been shielded and protected from lightning strikes and inside a chain link fence, and so it can't be vandalized. But if you make poor wiring connections, that'll shut the system off independently of all the other things. And the anode current density is limitation is something that they've identified for the mixed metal oxide. You have 110 millivolts per, or milliamps per square foot of mesh and mesh surface, and that current density, if you follow that, will not create acid. I'm sorry, I got to back up again. The concrete corrosion protection can be achieved at lower current densities than pipelines. That's another very positive thing. Initially, they were running these systems at a really high current density, very similar to pipelines, which are being protected by impressed current and galvanic systems all over the country. Impressed current cathodic protection can repassivate reinforcing steel, which is very unique because reinforcing steel is in a very alkaline environment, and you didn't see the same type of behavior in soil with pipelines. Nothing passivated; it would just, it would just become, it just didn't corrode. Now, what I'm talking about is repassivation. Is if you reestablish the passive film on the rebar, you can turn off your impressed current system for a year or something or more, and it still won't have any corrosion activity. So this generation of hydroxyl at the cathode reinforces the naturally occurring passive layer on rebar in concrete. Then we have this potential for hydrogen embrittlement for post-tensioning steels if it is not controlled properly. We're not going to get into that here today, but normally post-tensioning steels are a higher alloy, they're stressed a little bit higher, and they will become brittle if you run the potential of the steel too high. If it becomes greater than minus or more negative than minus 1.3 volts, the steel will become an electrode and will break down water into hydrogen and oxygen. And when you create hydrogen at the cathode, it will seep into the steel structure and can make it more brittle, causing it to fracture instead of yield. The criteria for cathodic protection are in these different standards. These two NACE standards are specifically for reinforced concrete, and these other standards, well, the ISO 12696 is for steel and concrete. The other two will cover steel and concrete, but it's mostly for marine structures. But they have the same fundamental criteria. If the potential of the reinforcement is greater or more positive than minus 200, the steel is passive, so you don't need cathodic protection. If the potential of the steel is greater than, well, more negative than minus 850 millivolts, you have achieved full cathodic polarization, which means there's no corrosion activity, and you've consumed the oxygen that's available at the cathode, so you've got a full cathodic polarization and no corrosion can occur in that environment. And this is only after consideration of IR drop between the structure and the reference electrode, because there is current flowing through the electrolyte. The distance between your reference electrode and the structure, there will be a resistance, and if the current is flowing, the V equals IR means you have a voltage drop across that soil, and if it's 10 millivolts or 15 millivolts, you have to add that to the 850. Or you can interrupt the circuit and take your measurement. It's what's called an instant off potential. So if you have minus 850 with an instant off potential, you're good to go. And the most important, most commonly used criteria is 100 millivolts polarization criteria. And that's between the native or non-energized potential of the reinforcing steel and the polarized potential. So if you start out with 300 millivolts as a native potential and you polarize it to 400 millivolts, you have achieved the criteria for cathodic protection. So on a modern bridge deck, what we have is a double layer of reinforcing steel. Normally there's an electrical bond between the two, and that can be from rebar hooks, it can be from standees, it can be from a lot of different reasons, but this is something you need to verify. And if the top steel and bottom steel are not electrically connected, you need to make them electrically connected. With a normal bridge deck, there will be some deterioration on the riding surface. So you remove that material, you expose the top reinforcing steel, you make your connections to the reinforcing steel, your wiring connections so that'll get to the rectifier, and then you put your mesh down and you connect that to the positive side of the rectifier. So a candidate deck is going to be a sound concrete deck with deep chloride penetration. So if you have chloride penetration from the top surface and it passes the reinforcing steel, it will be a good candidate for cathodic protection because there's nothing that can stop corrosion of the reinforcing steel once it's past it other than cathodic protection. If you've got chlorides that are past the rebar, there's really not much else you can do except for cathodic protection to stop it. In the systems that we have are overlays, you can do a slot system, you can do a soffit system. And a soffit system is typically a coating, a conductive coating that's placed on the bottom, or it could be a metallized surface. You can spray zinc directly on the bottom surface of the concrete. We aren't going to talk about those types of systems today, but those can also be used as anodes to protect your deck. Wiring can be susceptible, and we have to make sure we make good wiring connections and we protect our connections. So that's really important. And the thing you want to think about for bridge deck systems or the impressed current cathodic protection is that these are global solutions. You are protecting the entire surface of the entire deck is all part of it. The electrons do not know that you want them to go to this address or just show up here on the top steel. They're going to go to the top steel and they'll go to the bottom steel. And if you want them, you just can't tell them where to go. They will find their way. And if you have a surface applied or a overlay, the steel that's closest to the anode is going to get a large proportion of the current. So you have to factor that in. You may need to put in a little higher current for the system, just so that the bottom steel can get some cathodic protection. Typically, your cathodic protection is run with 1 to 2 milliamps per square foot. That's what your design current density, your cathode current density is, which is equivalent to 10 or 20 milliamps per square meter. And the anode current density is 110 milliamps per square foot. And beyond that, the concrete will acidify. So you want to keep your current density down on the anode. So we have to check the current density on the reinforcing steel and on the anode. So here's your a picture of an overlay system. This is on a sidewalk area, and you can see they've patched this slot here. I'm not sure what the slot was for. It could have been a continuity groove where they're connecting all the reinforcing steel, and they would weld it and then they'd patch it back. And then they put the mesh down, and you put little plastic pins to anchor it to the surface, and you cut away around any of these metals. So here you see this is a guardrail foundation. This mesh should stay a good 2 to 3 inches away from any of these metals. Sometimes, a lot of times, people use 6 inches. So you just want to make sure that it's spaced out and there's no chance that this anode will contact that embedded metal. Otherwise, that'll create a short. And here's what I was talking about. If you look at the resistance, you see here the current is flowing from the anode to the reinforcing steel. The concrete between the two, there's shorter distance for the current to flow through the concrete. So there's less resistance here. More current goes to the top steel than to the bottom steel. On a bridge deck, you'll come in here, you'll clean off the entire deck, you'll hydro demo the surface, you'll fix any potholes, any delaminations. You're going to verify the rebar is electrically continuous. If it is not electrically continuous, you will make it electrically continuous. And then you're going to install your reference electrodes and structure connections, and you locate wiring ports so that you can get your wires in an accessible location under the deck. Your reference electrodes are, this has a cap under here, and under this is a ceramic tip, and these reference electrodes get drilled and grouted into the concrete surface. And you normally have 2 to 4 per zone. Sometimes you can have as many as 8. It all depends on how you're going to monitor the system. The preferred way of installing reference electrodes is to do a half cell potential survey, identify the areas that are most anodic or the ones that have the most corrosion activity, place your reference electrodes there, and once you turn those most active areas cathodic, you have achieved your objective for the system. The other way is to put them in predefined locations so that they're easily identified and located for future access. Structure connections are just simply this. It's just a wire you found the reinforcing steel, they connect it to the reinforcing steel, and then they fill it with epoxy. You fill around the connection with epoxy so that no moisture can reach the copper to steel connection and cause a corrosion cell, a little mini corrosion cell right at that connection. And then you cut a slot and you run these wires through conduit down below the slab. And this is what it looks like from underneath. Here's where you brought in all your connections. This is a location where they put a reference electrode a little bit off to the side. Here's where all your wires come together and they go back to the rectifier. And this is what your rectifier looks like. This rectifier has 6 zones in it. This is a rectifier cabinet, and it has 6 different transformers taking AC to DC, and that's how it's split up. All your wires come in, and they are all your monitoring goes on here at your rectifier cabinet. Now, once you get all the wiring in place, you run the mesh on the surface, and they come in these rolls. Each roll is about 4 feet wide, 50 meters long. That's 162 feet. And those rolls are either touching each other, or they can be up to 6 inches apart. Typically, they're run right next to each other, and a transverse conductor bar connects them together, and you apply your current to your copper wires are connected to your conductor bar, and that distributes the current through all the titanium mesh. So then we put these plastic anchors. Well, you put about 1 foot on center on the edges and 2 feet on center through the middle, and they hold the mesh in place while you drive over it with your concrete trucks. A lot of times you'll put plywood down over top of the mesh so that the turning of the tires doesn't rip up the mesh, and the like. So you'll either put a fabric, sometimes a curing fabric can be used, or you'll put plywood sheets and you'll make these runners, and then as the concrete trucks dump their load, you'll pull a couple sheets of plywood and you'll just progress down the line. And a lot of times these overlays are done the same way you do a standard overlay, with a bed well, placing screed, and it's normal concrete construction once you get the mesh in place. Now, bridges also have substructures, and for substructures, we have a lot more reinforcement, and you have reinforcing cages. So you have different situations, like on the left here, they're using ribbon anodes to protect these girders, and this means you have a ribbon anode on the side that you see, and there's a ribbon anode on the opposite side, so that you can throw current evenly to both layers of reinforcement. The other way is to drill in anodes, and that's what these guys are doing here. They have drilled in ceramic tubes that go into these slots, and they're connected with titanium wires that get run in this slot down to a collector, and they're connected up to a rectifier. Everything gets the same kind of system. Is you have a anode, you'll have a conductor bar that connects to the copper wires, and the copper wires run back to the rectifier. Here's an example of mesh being installed on a plinth. And here they're just drilling in these little plastic anchors, and you can see the little plastic anchors here. Here's a little plastic anchor that's, oh, sorry about that. This little plastic anchor holding down a conductor bar. And you're just going to use a resistance welder. You see, this is the welder. Resistance welder, you're connecting the conductor bar to the mesh, and it's a very quick, it's a spot welding application. It's not a stick weld. All you're doing is applying electrical current. You're melting the mesh and the titanium conductor bar together. In this case, we're doing a plinth, and this is inside of a little cofferdam. You can see the mesh is placed, then they run a conductor bar all the way around to connect all 4 sides, and then they have wires coming off the side right here at the connection to the conductor bar. Then they put a reinforcement cage around it, and that reinforcement cage has to be verified that it is not touching any part of the impressed current system, or there will be a short circuit. You need to make sure, that's part of the quality control. You absolutely need to make sure no reinforcement or tie wire touches the mesh. Same thing goes with the ceramic anodes. These are ceramic anodes that are drilled in. These guys are looks like they're making kind of a mess, but this is a grouting operation where you grout the anodes into holes that are drilled in the concrete. The holes are verified that they don't hit reinforcing steel. There's a borehole probe that we use, and then there's a slot that's cut between them, and that conductor bar is welded to these titanium wires that feed the ceramic anodes. This little plastic tube is a vent. This allows moisture and chlorine gas from to escape from the concrete. That allows these types of anodes to go into systems that will be coated afterwards. They may coat this column once you install all the anodes. Excuse me. So the reason you're using a ceramic anode is you're going to place these anodes between the reinforcement layers, and that allows you to throw current evenly to the different types of reinforcement. So in this case, you see there's an anode placed between every other bar. This anode will throw current primarily to these two, this anode to these two, and this is how you would be protecting a single layer of steel. Now, if you have two layers of steel, you'd probably run this anode in a little bit further so that it's between the two layers of steel. In this case, you can see the anodes are placed, and they did it in a staggered fashion on this wall. And this wall was, the reason they did it here was they used salt, it's chloride contamination in the mixed water to begin with. It was, I don't know if it was mixed water or if it was the sand. I think it was a chloride contaminated sand that happened, and so they had to put impressed current in this relatively new structure. This is an application on a cooling tower. This wall is 3 feet thick. This shows you where you place your anodes. This was what I was talking about. You put the anodes in the middle of the wall. They throw current from here. Oh, let me back up here. Yeah. They throw current from the anode to the reinforcing steel in a very even distribution pattern all around. So you have current throwing from the anode onto the reinforcing steel. And the key to cathodic protection design is designing the current distribution so that you have it distributed evenly throughout the structure. In this, here you can see where the X's are, that's where they're going to drill holes, and all the red is the reinforcing steel. So you can see there's quite a bit of reinforcing steel that they had to navigate around. And this is a completed installation. You can see the vent tube, you can see the wire coming out, and here the titanium wire is welded, is spot welded to a current conductor bar. And here's just a video from the installation. You can see they went in quite a ways to get the anodes installed. This is a close-up of the current distributor bar and the titanium anode wire being welded. You see how it's spot welded at multiple locations? That's how we do it. Here's a ribbon anode system. This was a replacement of one of the original slotted wire systems. And what we did is we came in, we cut out all the old, well, some of it you could pull out, but a good bit of it we had to cut out. And then we checked for shorts, checked for low cover reinforcement, and we masked off those areas with epoxy. Then we installed our conductor bar, our ribbon and conductor bars. Here's your ribbon being welded to a conductor bar. And then we tested it, checked for shorts. Once everything passed QC, we grouted it in place. Once we had it completely grouted in place, then they came over the entire surface, shot blasted the entire surface, and put a coating over the top of it. Here's another unique application. This is over the Big Dig tunnels in Boston, and we had a set of transfer girders that was to hold up a apartment building columns. So, and this is directly over top of the tunnel. And you can see here we use fiberglass reinforcement and to make a cage, and we tied our ribbon anodes to these cages, and these cages go inside. Here's the transfer girders. These cages went inside these little pockets. These were all filled with flowable fill. And you can see the wiring is done here. And then once this flowable fill was installed, they poured a concrete slab across the top here, and they waterproofed it. And so we had one chance to protect this structure, and that is before they poured any of the flowable fill, because this thing is never going to be able to be seen, or you can't get back to it afterwards. And so this being the foundation of a building, they wanted to make sure it was be there for 75 to 100 years. So we put a cathodic prevention system in, and it's working just fine. Another way to do it is you can use these ribbon anodes in new construction. This is an application where we rebuilt the top of a cooling tower, and we put the ribbon anodes in the very top one where we rebuild it, so the entire structure is protected with cathodic protection. So there's another layer of reinforcement that would go in front of this. So this ribbon anode is placed between the layers of steel. And once we get it all back down to the rectifier, we have all the wires into the rectifier. We need to control it, and we need to record the data using remote monitoring. And remote monitoring is, today's systems are so much more user-friendly than what they used to be. They used to be required, landlines and cell numbers and all that kind of stuff. And now this will automatically dial into the internet, save it onto our server, and it does it twice a day. It'll collect it, twice a day. Sometimes you can do it 3 or 4 times a day, depends on what the needs are. But a lot of times you're just going to run it morning and night. Pick 2 times. Could be 6 o'clock a.m. and 6 p.m., or it could be midnight and noon. Do it however, whatever times you think are necessary. And the cellular and satellite communications allow you to put these systems anywhere. They give you alerts whenever the text, in a text message, structure A, zone B has overloaded. You need to check it out, or you lost power. You'll get all sorts of little text messages sent directly from the remote monitoring unit. And the automated data collection gives you better data over the life of the system, which is superior to manual data, because manual data is kind of like a snapshot in time. And if you can get the automated data, you can see how things are behaving through different temperature regimes. You can see how temperature affects it. You can see how moisture affects it. All this stuff shows up in your data, and also, you can remotely depolarize and interrogate the system by use of these. What we have here is relays that are triggered by the our program, and it'll say, all right, on the first day of every month, let's turn off the system and depolarize it and see what the potentials are, and we'll take a group of depolarized measurements. And that's a pretty easy and pretty common way of doing it. And this is what the output looks like. This is a cooling tower project I was telling you about earlier. We have all these different zones, and you can just click on one of these. If you want to click on this reference, it would give you the history of that reference electrode in a graphic format. You want to see what the voltage supply is for this zone and what the current is for this zone. You just click on these two, and it'll automatically graph it for you and give you all the data that is stored for that sensor. And we can log into it. Normally we give a manager, a facility manager will have access to this, so they can log in anytime. For this cooling tower, the control tower is has access to it. They can see you can see all the zones. They don't normally have to mess with it much because we manage it. And this is the type of thing that we do. And if you have any questions, now's the time.
Thanks, Matt. There's one thing I know about you. When you're asked for a dime, you supply a dollar. That was very, very thorough. We do have some questions from the audience here, and I'll just bring up the first one from our friend, longtime friend of the show, Zaire. He's asking is it true that impressed current will increase the stiffness of steel? Now, I think he's probably referring to your comments about hydrogen embrittlement.
It will not increase the stiffness of steel. What it will do, it can embrittle it, and it won't change the stiffness. The hydrogen embrittlement will make it more fracture sensitive. So if there is a defect, it will want to fracture. And it's not very common that you see that. And you have to really run it for a long period of time at a very high level for that phenomenon to occur.
Okay. Second question is from Bert. Do you get faster acid formation with titanium ribbons when they get wet?
No. It all depends on how you're running the system. If you have a rectifier that is set for constant voltage, it will fluctuate. It applies the same voltage. So as it gets wet, more current will be delivered. If you have it on constant current, then if it gets wet, the voltage will drop. But if it gets dry, the voltage will rise. And when the voltage rises too high, then you can get more acid generation because you're breaking down water.
Okay. Marcella is curious about the interesting topic of ASR, alkali silica reactivity, or AAR. Could you talk a little bit about the use of CP in concrete when this condition, ASR, AAR, is present?
Well, I've addressed this on a couple different projects, and what we're trying to do then is to make sure that we do not over polarize. You need to keep your system dialed in and controlled so that it stays under a volt. The polarization of the reinforcement stays under 1 volt. And if you do that, you won't be generating excess alkali around the reinforcement, and it will not trigger the ASR. But if you run it uncontrolled, it can potentially increase the pH around the reinforcement enough that will trigger ASR in the sands or in the aggregates close to the rebar.
Thank you. We're getting close to time here, so just maybe a couple more questions. NC is asking, with top and bottom mats as shown on the diagram that you had, how much protection of the bottom mat can be achieved with a top surface mounted anode? So say, for example, in a parking garage or in a bridge where the bottom mat is of concern, but the top mat isn't, how much can you really deliver from a top mounted system?
Well, like I said, it all depends on the reinforcement density and the thickness of the slab. Typically, you're in that 70 to 75% of the current will go to the top layer of reinforcement. If you are in a parking garage and you have a 8-inch thick slab and you have bottom reinforcement that you're concerned with, you probably should put in a soffit system, so that it will address the corrosion directly on the bottom surface.
Awesome. We have a lot more questions here, but we won't be able to get to them, and I'll address that in 1 second. I just had one last question for my own interest. We've had 9 webinars now describing all kinds of tools and systems for protecting bridges from corrosion. So we've discussed galvanic anodes, and you have today as well. We've discussed a new kind of called a fusion anode that does have an impressed current component to it. And then we've now discussed impressed current cathodic protection. I know every tool has its place in your tool belt, but where does impressed current fit in your mind? Where is it best suited, most cost effectively used?
Like I mentioned earlier, it's a global solution. Where you see a benefit for impressed current is if your structure is essentially sound, it is contaminated, and you want to protect the entire thing, and you want to get the maximum amount of service life out of that structure. So the cost is really relative to the amount of life that you're going to get. If you do a targeted galvanic anode approach, that's going to protect the area that's corroding today, but it's not going to stop the area 10 feet away from corroding in the future. You put a cathodic protection system, pressed current cathodic protection system over the entire structure, it protects the entire structure, and the whole structure doesn't corrode for the life of the system. So it could easily give you 30 to 50 years extra life if the structure can structurally manage it. And the problem with bridges is in 50 years, they become functionally obsolete, not as much structurally obsolete,
Absolutely. Thanks, Matt. I really appreciate you taking the time today. I know we didn't get to all the questions. There are at least 10 more that we didn't get to. So for those of you who still have questions, please do not hesitate to reach out to Matt directly here. His contact information is on your screen. I know he would love to chat with you about all your questions about impressed current or any other area of concrete preservation. So coming up, as I mentioned before, all the recordings from all our presentations will be on the Concrete Preservation Alliance website at safestructures.info, and registrations for upcoming webinars are there as well. We have on May 12th, we welcome Dave Whitmore back for a second time to speak about electrochemical treatments to extend the life of corroding substructures, followed by surface applied cathodic protection of substructures with Travis Marmon. And there's one more coming up in July, so we hope you can join us for all of these presentations. We hope this has been valuable. Thank you again, Matt, for dedicating your time to us today. This brings us to the conclusion of our presentation. Be safe out there, and good luck in saving some structures.